started with the sheet. By and large, I can see people are pretty actively involved doing the sheet, and you've been able to solve a few problems independently as well, right? So with the previous sheet and some problems from the sheet that are there in your kitty, you've got some warm up on kinematics. Now, even before I proceed solving the problems you have not been able to solve from the sheet, I want to get you acquainted with yet another notion. Now, if this is the origin O, and I measure positions from this origin O, positions of various particles are measured with respect to this origin. If there is a particle here, particle A, then this measures its position vector RA. OA measures the position vector of the particle A. If there is a particle B here, then OB measures the position vector of B, which is RB. That means if A is looked upon as an observer, then the position of A is measured with the help of the position vector RA. Position of B is measured with the help of the position vector RB. Yes or no? Right? However, if A is looked upon as an observer, if the observer is A, then A would not say the position of B is RB. A would say this is the position of B. This is the position of B as seen by A, right? Which is like if A is looked upon as an observer, then this is the position of B as seen by A, right? So AB the position of B as perceived by A. Or relative position of B with respect to A, or also referred to as relative position of B with respect to A. And very clearly from triangle law of vectors, by this time you would realize that this vector AB is going to be RB minus RA. This vector from triangle law of vectors is like RB minus RA. Right? Yes or no? Which is position of B with respect to A, which is written as RB with respect to A. Position of B with respect to A. Right? Position of B with respect to A is this vector AB, and is going to be, like I said, RB minus RA. Right? Now, velocity of A as seen by an observer at the origin. Velocity of A as seen by an observer at the origin would be measured by how RA changes with time. Right? Rate of change of RA with time will measure the velocity of A as seen by O. Yes or no? If there is an observer here, then velocity of A as perceived by the observer O is going to be how RA changes with time. ddt of RA. Velocity of B is measured by how RB changes with time. How RB changes with time. Yes or no? Velocity of B as measured by O, which is VB as seen by O, is how RB changes with time. Yes or no? Clear? But velocity of B as seen by A will be measured by how RB with respect to A changes with time. Yes or no? So velocity of B as seen by A, velocity of B as seen by A is going to be measured by how RBA changes with time. ddt of the position vector of B with respect to A. Right? Which is like ddt of RB minus RA, which is essentially ddt of RB minus ddt of RA. Right? Which is velocity of B as seen by O minus velocity of A as seen by O. Yes or no? Right? So this is going to be velocity of B as seen by O minus velocity of A as seen by O. This gives me velocity of B as seen by A. This is velocity of B as seen by A. This is also called the relative velocity of B with respect to A. It's also called the relative velocity of B with respect to A. Relative velocity of B with respect to A. Now, what it really means is, can I wipe this off? Can I wipe this off? If A is this, and say A has a velocity VA as seen by an observer at O, right? And B is this, right? And say B has a velocity VB as seen by a certain observer O. Clear? Then, when I say velocity of B with respect to A, what does it actually mean? That's important to understand. Velocity of B relative to A, velocity of B with respect to A, velocity of B as seen by A. It really means, see, if A is an observer, he doesn't perceive any motion in himself. It's as if A is at rest and B is moving with a velocity which is velocity of B as seen by A. This is what it means. That means this situation is equivalent to saying, if A is an observer in an equivalent environment, we can imagine A to be at rest, as if A is at rest. If A is imagined to be at rest, then the velocity of B would be the as seen by A would be the velocity of B with respect to A, and that turns out to be VB minus VA. That means the difference between the vectors VB and VA. Yes or no? Now, which means A perceives the velocity of B as the difference VB, and if this is VA, then realize that this would be minus VA. This vector would be minus VA, yes or no? This vector would be minus VA. So if this is minus VA, then The resultant of these two vectors would be VB plus minus VA, right? And the resultant of these two vectors could be obtained using, let's say, parallelogram, for example. That's one way to obtain the resultant. And this resultant using parallelogram law of vectors will give me the resultant of VB and minus VA. And this vector then would be like VB minus VA, which is velocity of B with respect to A, velocity of B relative to A, relative velocity of B as seen by A. It's as if A is an observer, it's as if A is an observer and B is moving with a velocity VB minus VA, right? It's as if this situation is equivalent to A being an observer. When I make A an observer, it's as if A is at rest. If A is an observer, it's as if A is at rest. And then if you ask A what the velocity of B is, A will not report a velocity B. A will report a velocity VB minus VA as shown by this diagram. Right? This is the velocity reported by A. When A reports a velocity, it's as if A is at rest and B is moving with a velocity VB minus VA along this direction. Yes or no? Right? Now, and what does it measure? If A is an observer, and say if this was the velocity of B as seen by A, and B was at some position B here, then it's as if A is at rest and the relative separation vector, this is the relative separation vector, this is the position of B with respect to A, and this is how the position of B with respect to A looks at different instants of time, right? Because B seems to be moving along this line as perceived by A, and therefore as perceived by A, it's as if A is pinned, it's as if A is fixed, and B is moving with the velocity of VB with respect to A, and therefore the position of B with respect to A, this is how it changes. This is, let's say, at some t equal to 0, the position of B with respect to A. This becomes some other position of B with respect to A at a later instant. This becomes velocity of B with respect to A at some other instant, and so on and so forth, right? So these are various RBA as seen by A of B at various instants of time. Yes or no? Right? So when we talk of position velocity of B with respect to A, then velocity of B with respect to A is how the relative position between the how the relative position between B and A changes with time. That is what measures relative velocity of B with respect to A. And similarly, if A had an acceleration A of A, and B had an acceleration, say A of B, as seen by some observer O. These are the accelerations of A and B as seen by an observer O. Then we define acceleration of B with respect to A. As, first of all, what's the velocity of B with respect to A? Velocity of B with respect to A is VB minus VA. That's the velocity of B with respect to A, right? The acceleration of B with respect to A would be obtained when you differentiate this. That will give you acceleration of B with respect to A, right? So the acceleration of B with respect to A would be obtained as ddt of VB minus VA Yes or no? That'll give me acceleration of b with respect to a ddt of this. That means ddt of their relative velocity will give me relative acceleration. Rate of change of relative velocity will give me relative acceleration, right? Which is like ddt of Vb minus ddt of Va, right? Which is ddt of Vb minus ddt of Va, which is ddt of Vb would give me acceleration of B, rate of change of velocity of B will give me acceleration of B, this will give me acceleration of A. So acceleration of B with respect to A is acceleration of B minus acceleration of A. That will give me relative acceleration of B as seen by A. Clear? Now, see, realistically, it's about when we talk of relative velocities and relative acceleration, it's suddenly as if we are thinking of a change of observer. It's as if we are thinking of change of observer. That's what we are trying to perceive. And relative to a new observer, we are trying to reduce the acceleration and velocity of various particles involved in the scenario. That's what we are trying to do, right? In the domain of the new observer, and if there is an observer, then with respect to that observer is at rest. It's as if that observer is pinned, right? So, a regular situation which you would have seen, if there is a particle A, and there is a particle B, say B moves to the right with a velocity of 20 meters per second along the x-axis, and A moves to the right with a velocity Va of 10 meters per second. Even though there is a fixed observer here, so there is a fixed observer here, this observer would report on A velocity of 10 meters per second to the right, would report on B a velocity of 20 meters per second to the right, right? Now, for A, what does this velocity mean? This velocity will tell you how OA is changing with time. This velocity of B as seen by O will tell you how OB is changing with time, right? If A is looked upon as an observer, if O is looked upon as an observer, then these velocities VA and VB will be a measure of how OA and OB change with time, yes or no, right? But this could also have been reduced to A being an observer. This could have been reduced to A being an observer, right? If A is looked upon as an observer, then that means in an equivalent, this is an equivalent situation in which A is our new observer, and as if A is at rest, that's why equivalent, as if A is at rest, and B moves to the right as seen by this observer. This observer will not report on B a velocity of 20 meters per second, because he will report on B a velocity of 20 minus 10, which is 10 meters per second. So velocity of B as perceived by A is no longer going to be 20. Now they are in the same direction, so vector difference is the same as scalar difference. If they were in different directions, we would take a vector difference of VB and VA. Since they are in the same direction, we'll take a scalar difference of VB and VA. Yes or no? Right? So velocity of B as perceived by A is going to be 20 minus 10. That makes it 10. Which is 10 meters per second. Now, what does this 10 meter per second measure? This measures how AB changes with time. This measures how AB changes with time, rate of change of AB with time, where A is actually not fixed. A is moving, B is also moving, but AB is changing at the rate of 10 meters per second. In this case, AB is increasing at the rate of 10 meters every second, right? So relative velocity will measure how relative separation changes with time. Yes or no? So this relative velocity will measure how this relative separation changes with time. Yes or no? Right? Now, so essentially, if the separation between A and B was originally 50 meters, then in the equivalent situation, at time t equal to 0, the separation between A and B is 50 meters. And if I look upon A as an observer, that means I'm forcing A to be pinned at its position. I'm forcing A to be pinned at this very position. And that means this is an observer pinned at this position, right? And I'm causing B to move now with a velocity. If A is looked upon as an observer, I would have to remedy the velocity of B. The velocity of B will no longer be VB. It's going to be VB minus VA, right? The moment you choose A as an observer, the velocity of B will no longer be VB. It's going to be VB minus VA. That's the revised and the modified velocity of B in an observer frame fixed to A. Clear? So that's going to be 10 meters per second, like I said. Velocity of B as seen by A, which is 10 meters per second. Now, so if A is looked upon as an observer, A is fixed, and now the velocity of B is no longer VB, it's V of B as seen by A, and it's 10 meters per second. So then, time in which the separation will change to 100 meters. Well, every second, it increases by 10 meters. So it will increase by another 50 meters in 5 seconds. It will increase by 50 meters in another 5 seconds. That means in another 5 seconds, the separation will become 100 meters, right? However, if I reduce a problem to its equivalent relative velocity state, this is the equivalent relative velocity state. This will truly indicate the separations between the two particles at various instants of time, right? The relative separation will be indicated by the relative velocity equivalent. This is the relative velocity equivalent, and at all times it will indicate truly the relative separation between the two particles. However, it will not readily indicate the true positions of the particle. For example, 5 seconds later in this position, if this was t equal to 0, say this was if this was t equal to 0, then say at t equal to 5, it's as if A is still at rest, A is at this position, and it's as if B comes to this position, B prime, where the separation between them becomes 100 meters. But is from this original position of A, is B actually 100 meters away? No, because A is neither at this position, B is not at this position. A would have advanced in 5 seconds by 50 meters. By 50 meters, B would have advanced by 100 meters. So the new separation would have increased by 50 meters. The new separation would have become 100 meters. But in the equivalent relative velocity situation, it will not tell me exactly where A is or where B is. B is not 100 meters from this position 5 seconds later. Right? 5 seconds later, B would have traveled 100 meters, and then from this original position, it would have been 150 meters. Yes or no? Right? So when you attempt to reduce a problem to its equivalent relative velocity problem state, then what you're sacrificing is the actual positions of the particles involved. Right? Actual position of A and B are not what is shown by the equivalent relative velocity diagram. But there are situations in which the actual positions of A and B don't matter. If there is a situation in which all that matters is the relative separation between A and B, no matter where A is, no matter where B is, if all that matters is the relative separation between A and B, then the equivalence of converting a situation into its relative velocity diagram, relative velocity situation would be justified. You know what I'm saying? Say, just to reiterate this one more time to give you some mental solace. Say, this particle moves to the right. Let's say particle 1 moves to the right with a velocity of 30 meters per second. This particle 2 moves to the right with a velocity of 15 meters per second. And the separation between the two particles is, say, 150 meters. Right? And I want to find the time. See, 1 is moving faster than 2. So 1 would eventually catch up with 2. 1 would eventually catch up on 2. And if I want to find the time it takes for 1 to catch up on 2, that means their relative separation to become 0. If 1 catches up on 2, what happens to their relative separation? It becomes 0. What is their initial relative separation? 150 meters. Right? So then, for 1 to catch up on 2, the actual time taken for 1 to catch up on 2 will not involve the actual positions of A and B. That's not important. The relative positions will then acquire prominence. That means, let's say, this situation could be reduced to its equivalent situation as follows. I look upon 2 as an observer. I look upon 2 as an observer. That means I am pinning 2 down. That means I am pinning 2 down. And then if I pin 2 down, that means I am reducing the velocity of 2 to 0. Then I want to modify the velocity of 1. The velocity of 1 will no longer be V1. Will no longer be V1. It's going to be V1 minus V2. Velocity of 1 with respect to 2. If I'm pinning 2 down, that means the 1 will no longer have a velocity V1. It will have a modified velocity which would be V1 minus V2, where V2 is the velocity of the observer. Who's the observer here? 2 is the observer here, right? So the velocity of 1 will no longer be V1. It's going to be V1 minus V2. That's the velocity of 1 as seen by 2. That's the velocity of 1 as seen by 2. As seen by 2 means I have assumed 2 to be at rest. If I have assumed 2 to be at rest, then the velocity of 1 will no longer be V1, will be V1 minus V2, where V2 is the velocity of the new observer, assumed to be fixed or pinned. Clear? So then, this then becomes 30 minus 15, which is 15 meters per second. And the separation between them is 150 meters. So the time it takes for 1 to catch up on 2 would be 10 seconds. Isn't it? 150 by 15. Time taken for 1 to catch up on 2 is going to be the relative separation. How much does the relative separation change? When 1 catches up on 2, it changes from 150 to 0. So what's the change in relative separation? 150. And what's the rate at which relative separation changes? 15 meters every second. So how many seconds does it take? 10 seconds it takes for the relative separation to decrease to 0. That means for 1 to catch up on 2. How about it? Now in this is good for finding the time it takes for 1 to catch up on 2. It's good for observing and analyzing the relative positions of 1 and 2, but not good enough directly at least to locate 1 and 2 appropriately, because in this equivalent situation 2 is looked upon as being here only, but 2 has actually moved. In 10 seconds 2 would have moved 150 meters. So the actual position of 2 10 seconds later is actually 150 meters away from this position, because it was moving with a velocity of 15 meters per second. Yes or no? Right? So now it's another story. You could use this time to subsequently obtain the actual positions of 1 and 2. So in 10 seconds later, 1 would have been 300 meters from here, and 2 would have been 150 meters from here, if you want to actually deal with their absolute positions or their actual positions. But if it's only the relative position between 1 and 2 which is relevant and important for a physical requirement, then we look upon one of them as an observer. The observer is fixed, and the other one is caused to move with a velocity which is the relative velocity of this with respect to the observer. That's the equivalence that will guarantee the rate of change, that will bring to us the rate of change of their relative positions, not their absolute positions. Clear? Now, okay, so let me do that for you. Say, he's saying, treat 1 as an observer. Okay? So V1 was how much? 30, right? So he's saying, treat 1 as an observer, right? Okay. So 1 is treated as an observer. This is my observer. Then the velocity of 2 would have to be modified. It will no longer be 15. It's going to be V2 minus V1 as seen by this observer, right? It's going to be V2 minus V1 to the right. V2 minus V1 to the right means 15 minus 30 means minus 30 to the right. Minus 30 meters per second to the right is the same as 30 meters per second to the... I'm so sorry. Minus 15 meters per second to the right means 15 meters per second to the left. So it's as if O is an observer. Their original separation was how much? 150 meters. Right? If this is an observer, this is 2, which now has minus 15 meters per second to the right, which is the same as saying 15 meters per second to the left. And then the time taken for 2 to catch up on 1 would be 150 by 15, which is 10 seconds.
If we are not inverting the direction, suppose we say that V with this x1 is equal to minus 15, so the displacement also has to be minus 150.
So then minus 50 by minus 15, that will still be 10. So time taken is still 10 seconds for them to catch up.
How V minus V1 will become minus 150?
No, because physically it's fine, because velocity of 2 with respect to 1 is negative to the right. That means it's actually positive to the left. Think of it physically. It's negative to the right means it's positive to the left. No, without physical is based on physical only, right? So then the separation of 1 with respect to 2 is still 150, is positive only, because I'm measuring everything positive in this direction. So if 1 is an observer, you will measure it like this only, isn't it? Then it will be plus 150 only, and the relative velocity will be 15. No, it's 15 relative. See, this is V2 minus V1, which is minus 15 to the right, which is the same as 15 to the left. It is 15 to the left now. So then for this separation to reduce to 0, it will still be 150 by 15 only, which is 10 seconds. So far so good, right? Right? Now, say there is a particle P, hmm, that moves to the right with a velocity Vp, say. That moves to the right with a velocity Vp. Clear? There is a particle Q which at certain instant of time, you know, separation between P and Q is D, say, D naught. Separation between P and Q is D naught. Velocity of Q, say at this instant of time, is Vq. And say Vq bigger than Vp. Say Vq bigger than Vp. Now if Vq is bigger than Vp, subsequently Q would bump into P. If Vq is smaller than Vp, Q will never bump into P. But if the velocity of this is larger than the velocity of this, then they will bump into each other, right? And how do you find the time they take to bump into each other? The relative velocity divided by relative separation will give you the time it takes for them to bump into each other, right? What would be the time? What would be the time it takes? Relative velocity of Q with respect to P is going to be Vq. I'm sorry, relative separation D naught divided by relative velocity, which is Vq minus Vp. That's going to be the time it takes for Q to bump into P. Yes or no? Now, to avert a collision, what Q does is Q begins to have a retardation. Q begins to have a retardation. Retardation means it will have an acceleration AQ to the left, 5 meters per second squared to the left, and 10 meters per second to the right. Means velocity and acceleration are oppositely directed. That means it must be a case of retardation. 10 meters per second squared retardation means it's going to be 10 meters per second squared opposing Vq, opposing Vq. Now, the question is, the attempt is to avert the collision. Let me reduce this situation to an equivalent situation and see if the collision can be averted. Right? What I do is, I look upon P as an observer. That means I pin P down. Right? P is looked upon as an observer. That means I fix P. Now, at time t equal to 0, then, as seen by P, what would be the velocity of Q? Vq minus Vp. As seen by P, what would be the velocity of Q? Velocity of Q minus velocity of P. P is the observer, right? So in the equivalent state, the velocity of Q is going to be Vq minus Vp. Is going to be Vq minus Vp to the right, right? That's the velocity at time t equal to 0. That's the initial velocity of Q at time t equal to 0 as seen by P. At time t equal to 0, this is the velocity of Q as seen by P, right? Now, what is the acceleration of P? 0. Acceleration of P is 0. What is the acceleration of Q? AQ to the left. Is AQ to the left? AQ meters per second squared. AQ say is 20. So it could be 20 meters per second squared to the left. Right? Now, acceleration of Q as seen by P. Acceleration of Q as seen by P. That means the acceleration in this revised situation. Acceleration in this revised situation of Q as seen by P. That means relative acceleration of Q with respect to P. That's going to be acceleration of Q minus acceleration of P. Now, acceleration of Q. I'm taking everything rightward positive, everything leftward negative. So, acceleration of Q is going to be minus AQ. Suppose AQ was 20 meters per second, then along with its sign, it's going to be minus 20. Acceleration of Q then would be minus AQ. Minus AQ then, right? Is going to be minus AQ, acceleration of Q, minus acceleration of P. What is acceleration of P? 0. Right? So that's going to be minus AQ. That's the acceleration of Q as seen by P. Acceleration of Q as seen by P is going to be minus AQ. Yes or no? Right? Now, D naught is the separation between them. Where acceleration of Q is minus AQ. It's as if Q has a velocity VQ minus VP to the right, and it has an acceleration minus AQ, right? Constant acceleration. As seen by P, constant acceleration. So in this equivalent situation, I can apply S equal to ut plus half at squared for a constant acceleration case, where this S will be the separation between P and Q, that is the relative separation. U would be the initial relative velocity. A will be the relative acceleration. The relative acceleration is minus AQ. Yes or no? Relative initial velocity is VQ minus V naught, VP. Now, realize that as seen by P, Q has a retardation because its acceleration is minus AQ. So velocity of Q decreases. Yes or no? Let us find the time taken in this equivalent situation for the velocity of Q to reduce to 0. Can I not apply this? V squared minus U squared is 2AS. Right? For Q, velocity at some instant of time is given by V squared minus U. What is U? VQ minus VP. V squared minus U squared is 2. What is acceleration? Minus AQ. Minus AQ. Into the displacement S from this position into the displacement S from this position. Yes or no? Right? It's as if P is fixed. Q has a velocity, VQ minus VP to the right, and Q has an acceleration, minus AQ. Then the velocity of Q as seen by P at any given instant of time is going to be given by V squared minus U squared is 2 times minus AQ into S in this equivalent situation where P is fixed. Clear? Now, as seen by P, Q is retarded. Q is retarded. That means velocity of Q would become 0 sometime. This is V is the velocity of Q as seen by P at various instants of time. Velocity of Q will become 0 at some instant of time. Right? Let me find out the displacement of Q when its velocity becomes 0. Let me find out the displacement S of Q when V becomes 0. So when V becomes 0, everything referred to this equivalent situation, right? The displacement of Q is going to be VQ minus VP whole squared divided by 2AQ. Put this equal to 0. Then what would be S? S would be VQ minus VP whole squared divided by 2AQ. Yes or no? Right? S would be VQ minus VP whole squared divided by 2AQ. This is the displacement of q. This is the displacement of q till such time that the velocity of q reduces to 0. Right? In the equivalent situation. Forget all about this in this situation. In this situation, p is fixed. V has an initial velocity vq minus vp and has a backward acceleration aq. That means retardation, right? If this distance s exceeds d naught, then there will be collision. If this distance s that I have computed is less than d naught, there won't be collision. Yes or no? To avoid collision, this displacement of q should have been less than or equal to d naught. Right? If there was a collision, then this displacement s, right? Because see, if its velocity becomes 0 somewhere here, then its displacement s should have been less than d naught. Right? But if velocity becomes 0 on surpassing p, that means there must have been a collision. That means it reached p with a non-zero velocity, its velocity became 0 later on. Right? So to avoid collision, what is required? S must be less than or equal to d naught, where s is the displacement of q by the time its velocity becomes 0. Yes or no? Let me portray the whole thing with some numbers. Let me use some numbers to illustrate and give you a feel for what is actually happening here. All right. Say there is a particle A and there is a particle B. And their separation is, original separation is 100 meters, say. A has a velocity of 5 meters per second to the right, and B has a velocity of, say, 8 meters per second to the right. And their separation at this instant of time is 100 meters. Okay. Now, at this instant, B suddenly observes A. B would want to avert a collision with A. B would want to avert a collision with A. So B applies brakes. B applies brakes. If B didn't apply brakes, then since the velocity of B is larger than A, eventually B would bump into A at some instant of time. Yes or no? Right? So when he applies A, say B then has a retardation of say 3 meters per second squared to the left, has an acceleration of 3 meters per second squared to the left. I want to check if the collision could be avoided or not. Let's check that. Let me forget all about this situation, reduce this to an equivalent situation. In the equivalent situation, I would look upon, say, A as my observer, and therefore the velocity of A would be reduced to 0. That's an equivalent situation, right? So in the equivalent situation, I'll forget all about this original situation. A is pinned. At time t equal to 0, and at time t equal to 0, B has a velocity 8 minus 5, which is 3 meters per second to the right. That's an equivalent situation. Right? Now, acceleration of B would be what? As seen by A is going to be acceleration of B minus acceleration of A, right? Acceleration of B with respect to A is going to be acceleration of B minus acceleration of A. all with respect to A. Why? Because A is my observer. A is my observer. Acceleration of B. What's acceleration of B? I'm taking everything rightward positive, everything leftward negative. So acceleration of B would be -3. Acceleration of A is 0. Right? So that's going to be acceleration of B with respect to A. That means in the equivalent situation, this was the equivalent situation, B has a acceleration -3 meters per second squared. That means 3 meters per second squared to the left. That means 3 meters per second squared to the left. That's the acceleration of B in this equivalent situation. Clear? Now, the separation is 100 meters. Now I forget all about this. Can I remove the clutter from top and just focus on this? If someone gives you this problem to solve, if someone just gives you this problem to solve, then it's a case of constant acceleration of B. So I can apply V squared minus U squared is 2AS, right? So the velocity of B after it has got displaced by an amount S to the right, the velocity of B at some instant of time after having got displaced S units to the right is going to be V squared minus, what is U? U is 3. 3 squared is 2 times A. A is 3 to the left, that means -3, because I'm choosing to measure everything rightward positive and leftward negative. So 2 times -3 into S. That's the velocity of B in this equivalent situation after having got displaced S units to the right. What do you say? B, the velocity of B is very clearly decreasing while it's getting displaced further and further because it's getting retarded, as you can see. So in the equivalent situation, the velocity of B is mitigating, right? So velocity of B will become 0 sometime. Let me find out the displacement of B. Let me find out the displacement of B by the time its velocity becomes 0. Right? So when V is 0, the displacement of B is going to be what? -3 squared divided by 2 into -3. Yes or no? So that makes it 1.5 meters is what it gets displaced, right? 1.5. That means, B comes to this position, it gets displaced by 1.5 meters and its velocity will become 0. So S is less than 100 meters. So there is no collision. So there is no collision. Do you all understand this? Right? Raj? All's good? In a more general sense, say, if there is a particle 1, it has a velocity u1 at time t equal to 0 and it has an acceleration a1 to the right, right? And there is a particle 2, it has a velocity u2 and has an acceleration a2 to the right, right? It's my choice. I can make 1 as an observer or 2 as an observer, does not matter, right? So what's the equivalent situation? Suppose I make 2 as an observer. Suppose I reduce 2 to an observer. So this equivalent situation then is 2 pinned in position, 1 now does not have a velocity u1. In this equivalent situation, what would be the velocity of 1? u1 minus u2. What would be the acceleration of 1 in this situation? A1 minus A2. Yes or no? Right? Yes or no? Yes, right. Very good. So this becomes the equivalent situation to deal with. This becomes the equivalent situation to deal with. Now, say in a vector domain, that's a limiting case. It just brushes. It just brushes. That's all. So it's hardly an impact. That means by the time s becomes equal to d naught, it has just acquired zero velocity. So it's just touching it. So it's not harming it. So we say that it's a limiting case of collision. We call it a limiting case of collision when s becomes equal to d naught. Right? Okay. Suppose there is a particle 1, it has a velocity v1 that makes an angle 60 degrees with the positive direction of the x-axis. Say v1 is 5 meters per second. Right? And there is a particle 2 somewhere here. And it has a velocity, say v2 equal to 3 meters per second, like this. And say it makes an angle 45 degrees with the negative direction of the x-axis. Right? These are two particles and these are their velocity states at some instant of time. Clear? I now want to find the velocity of 1 as seen by 2. I want to find velocity of 1 as seen by 2. In situations of this kind, I will never recommend using parallelogram law vectors to do a vector difference. I would rather resolve the two vectors. So if you look at the velocity of 1, it could be resolved as v1 cos 60 degrees to the right and v1 sin 60 degrees upwards. Yes or no? How about it? That's resolving v1 horizontally and vertically. Look at 2. This is v2. This is 45 degrees. So this is v2 cos 45 degrees and v2 sin 45 degrees. Right? So we then say they have a relative velocity along the x direction and they have a relative velocity along the y direction. Right? So between these two velocities of these are the velocity diagrams of 1 and 2. We then say their relative velocity along the x-axis. They have a relative velocity along the, that means velocity of 1 with respect to 2. Velocity of 1 with respect to 2 along the x-axis is going to be velocity of 1 along the x-axis minus velocity of 2 along the x-axis. That means their relative velocity of 1 along the x-axis minus velocity of 2 along the x-axis will give me their relative velocity along the x-axis, right? What is the velocity of 1 along the x-axis? V1 cos 60 degrees, right? Minus. What is velocity of 2 along the x-axis? Minus V2 cos 45 degrees, because it's in this direction, negative x direction. I've chosen everything positive here, so everything here would be chosen negative. So velocity of 2 along the x-axis would be minus V2 cos 60 degrees, minus V2 cos 45 degrees. So velocity of 2 along the x-axis is minus V2 cos 45 degrees, right? That means that's going to be V1 by 2 plus V2 by root 2. That's the relative velocity of 1 with respect to 2 along the x-axis. What is it going to be? Velocity of 1 along the x-axis minus velocity of 2 along the x-axis. Yes or no? Right? Now, what is velocity of 1 as seen by 2 along the y-axis? That's going to be velocity of 1 along the y-axis minus velocity of 2 along the y-axis. That will give me velocity of 1 with respect to 2 along the y-axis. Velocity of 1 along the y-axis minus velocity of 2 along the y-axis. What's velocity of 1 along the y-axis? V1 sine 60 degrees. What's velocity of 2 along the y-axis? V2 sine 45 degrees. Which is V1 root 3 by 2 minus V2 by root 2. Yes or no? This is the velocity of 1 with respect to 2 along the x-axis. This is the velocity of 1 with respect to 2 along the y-axis. That means this is their relative velocity along the x-axis. This is their relative velocity along the y-axis. Okay. Which means if I have velocity of 1 with respect to 2 along the x-axis known to me, which is this, and if I have velocity of 1 with respect to 2 along the y-axis, which is this, right? Then the net velocity of 1 with respect to 2 is going to be given by this. Velocity of 1 with respect to 2 will be obtained by this diagonal of this rectangle. So velocity of 1 with respect to 2 then is going to be, suppose this length is a units, this length is b units, that's going to be given by root a square plus b square. And this relative velocity of 1 with respect to 2 will make an angle alpha with the positive direction of the x-axis. How do you find this alpha? Tan alpha would be this length a divided by this length b. Right? Clear? Now, can I wipe this off? Or you could have even vectorially written the two velocities, in the sense velocity of 1, if you want to write vectorially, what would it be? Tell me. V1 cos 60 degrees I cap plus V1 sin 60 degrees j cap. Yes or no? Right? j cap. That's the velocity of 1 written vectorially. Do you all understand this? Velocity of 2, if I have to write vectorially, what would that be? Velocity of 2 written vectorially would be minus v2 cos 45 degrees I cap, because it's along the minus I cap direction. So v2 cos 45 degrees into minus I cap, a unit vector in this direction would be minus I cap, right? So it's going to be minus v2 cos 45 degrees I cap plus v2 sin 45 degrees j cap right? And now if someone said, what's velocity of 1 with respect to 2, if you have to write vectorially? Velocity of 1 as seen by 2, that's going to be velocity of 1 minus velocity of 2. And velocity of 2 with respect to 1, that's going to be v2 minus v1. So now if you took a difference, then that's going to turn out to be v1 cos 60 degrees plus v2 cos 45 degrees I cap, right? And these two would constitute the j cap, v1 sin 60 degrees minus v2 sin 45 degrees j cap. That's velocity of 1 with respect to 2. One thing that you can easily see, velocity in all senses of the word, velocity of 1 with respect to 2 would always be minus of velocity of 2 with respect to 1. Always. Because this would be v1 minus v2, this would be v2 minus v1, and they are negatives of each other. And similarly, same thing for acceleration. Acceleration of 1 with respect to 2 will always be minus acceleration of 2 with respect to 1. Yes or no? No confusion, pretty simple, right? It's just that we are looking at a different observer. If we are looking at a different observer, we modify all other velocities commensurate with the new observer. The new velocities obtained are in a field which is perceived by the new observer, which is the relative velocity of all other particles, which is the velocity with respect to the new observer. Clear? Now, all's fine so far. Pretty simple stuff, right? Suppose there was a particle at a certain height above the ground, say h, all right, and it was moving up with a velocity, say 10 meters per second. And of course it has a downward acceleration g, right? It has a downward acceleration g. Say this h is 400 meters. And at the same instant, there was a particle which is launched up with a velocity of 30 meters per second. This also, yeah, from the ground. Right? Yeah, I mean, see, the point is, in one form or the other, keep energizing the class, even if it means a little playfulness, acceptable as long as you understand the extent to which the playfulness should be carried, right? In the event you don't understand where to draw a boundary, you would realize the consequences subsequently, because I would respond to that. I'm not inert to that. All right, I will act on it. I might carry a fake smile, but I'll use powerful words, right? Now, I want to find if this particle A catches up on B, and if it does, the time it takes to catch up on B. Both have a downward acceleration g. See, in this case, look at this equivalent situation. B has an acceleration g downwards. A also has an acceleration g downwards. Yes or no? Let me look upon B as an observer. Let me look upon B as an observer. So, in this equivalent situation, where B is looked upon as an observer, that means B is pinned. B is stationed. Clear? And the velocity of A at this instant of time is 30 meters per second. Velocity of B at this instant of time is 10 meters per second. Now, if I'm pinning B down, will I have to modify the velocity of A? What would be the modified velocity of A? 30 minus 10, which is 20 meters per second. That would be the modified velocity of A in the equivalent situation. Now, in the equivalent situation, look at this. The acceleration of B is g downwards. The acceleration of A is g downwards. What's the acceleration of A as seen by B? 0. Acceleration of A as seen by B is going to be acceleration of A minus acceleration of B, both g. So, g minus g, 0. Right? That means, if B is looked upon as an observer, A has no acceleration. If B is looked upon as an observer, A has no acceleration. Yes or no? Right? That means if A has no acceleration, A must be moving with a constant velocity. If A has no acceleration, A must be moving with a constant velocity in this equivalent situation. And then time taken for it to catch up on 400 meters. The time taken by A to catch up on 400 meters would be 400 by 20, that is 20 seconds. So, time taken for A to catch up on B is 400 divided by 20, that makes it 20 seconds. How useful this situation is. How useful this situation really is. Do you realize that? I don't have to do I don't have to create any algebraic discomfort for myself when I deploy this situation. When all that matters to me is, let's say, the relative separation between A and B, then reducing the problem to this equivalent state comes in very handy. It makes the whole situation very simple and versatile. Right? So, this is what. And then you don't have to apply S equal to ut plus half at squared, etc. and create ugliness in the expression. Right? If you are an observer and you find a particle to be moving with constant velocity. So, you are an observer and you find a particle to be moving with constant velocity. That means the two things that you report on the particle, number one, the magnitude of its velocity does not change. If it's moving with constant velocity, obviously its magnitude does not change. Number two, its direction also does not change. That means if its direction does not change, it must be moving in a straight line. That means if its direction does not change, it must be moving in a straight line. Yes or no? So even though the other particle could be moving in a very complicated actual path. But if you are an observer and you perceive a constant velocity on that particle, if you perceive a constant velocity on that particle because you are also in motion, say, then the path that you observe on the particle will be a straight line. What I mean is, say, there is a particle which is launched with a velocity u1 at time t equal to 0. At t equal to 0, there is a particle launched with a velocity u1 making an angle theta with the horizontal. Making an angle theta with the horizontal. Clear? And at this instant of time, there is another particle which is launched with a velocity u2, say making an angle alpha with the negative direction of the x-axis, say, right? This is particle 1 and this is particle 2, and both under the influence of gravity, vertically launched, so under the influence of gravity. Now if one is inquired about the path of 2, okay, realize that acceleration of 1 is g downwards, acceleration of 2 is g downwards, yes or no? So acceleration of 2 as seen by 1, acceleration of 2 as seen by 1 is going to be 0. That means 1 does not perceive any acceleration on 2. That means 1 finds 2 to be moving with constant velocity. That means 1 finds 2 to be moving with constant velocity. Yes or no? Right? So acceleration, vector acceleration of 2 with respect to 1 is 0. Right? That means velocity of 2 as perceived by 1 is constant. Because if it was not constant, the acceleration would be 0. Right? Is it bothering you, or are you comfortable with the thought? Right? So velocity of 2 as seen by 1 is a constant. That means 1 finds the velocity of 2 to be constant. That means 1 finds the velocity of 2 to be constant. That means 1 finds that the direction of velocity of 2 is not changing with time. That means 1 finds that 2 must be moving in a straight line. Yes or no? That means the path of 2 as seen by 1 is going to be a straight line. Even though the actual path is a parabola in the gravitational field, but if 1 is also in the gravitational field in some kind of a motion, non-zero motion, then 1 would find 2 to be moving along a straight line. How about it? Clear? So far so good, right? Stand by.